Right, now, you remember in earlier, several times in earlier sessions, we mentioned that in the future we would give an example of a proof by induction that that a particular machine that you generate, that you construct, proof by construction, that proof actually works as desired. Now, in the past, those machines, their functioning were pretty straightforward, so it didn't bother proving that they work as desired. But now finally we've come to the example that was referred to earlier. So 1.65, you may remember that number from earlier sessions. So now we have to bite the bullet. Now we actually have to do our first proof of functioning, that the thing that we construct actually does what we claim to do. And typically a proof of functioning of something you construct takes the form, that proof takes the form of induction, proof by induction, right? So what's the claim? We're going to prove that this machine, this here, that it actually does what it's supposed to do. And what is the claim? Now, Sipser uses the term claim. You could call it a theorem. I mean, because he has a proof, right? You could call it a theorem or a lemma or whatever. So but he just calls it a claim. I mean, it's somewhat different, I suppose, from a usual theorem, but it does have a proof. So, I mean, when I was counting up the number of theorems, including corollaries, in the textbook, I included claims because they struck me as being very theorem-like. Okay. So, what is the claim? What's the theorem statement? In other words, okay. So, it's just saying that any GNFA G if you convert G, when you convert G, what are you doing? Well, you get a regular expression. Right? That's the aim. The output of this. You input a GNFA, you put it into convert, and it will convert your GNFA, your formal description of a GNFA, into a regular expression that describes a language. That's what a regular expression does. Okay. So this regular expression that this generates is equivalent to G. Now G, what is G? G is an automaton, right? It's a machine. It's a finite automaton, a generalized, non-deterministic, finite automaton. It's an automaton. It's a machine. Okay. And convert G. What's that? The result. Well, it's a regular expression, right, which describes the language. Now, to say that the machine and this, which is a regular expression, that they are equivalent, well, that's sort of what we've been proving. But we have to prove that the use of this convert is actually doing what we want it to do. In other words, it's giving us regular expressions that are equivalent to G. Okay, that's what we have to prove. That we're trying to show that this works as desired. That's the point. So we have to prove that the regular expression given by this is equivalent to G, and the machine. And to do that we use induction, an inductive proof. Remember from our talk on induction before, it's a two-part proof. You do the base case, it's true for a small. An induction usually involves some integer, a parameter that goes into the induction, and you prove it true. Typically, say your integer in the induction is k. So typically you will prove that the hypothesis you're trying to prove by induction is true for k equals 1. That's the basis part here. And the other part, the inductive step, is you assume that it is true, the hypothesis you're trying to prove, you assume that it is true for k minus 1, and then prove, if it's true for case k minus 1, then it's true for case k. Okay? Well, that means then if it's true for k equals 1, then it's true for k equals 2. And if it's true for k equals 2, it's true for k equals 3, and so on. So you've proved it. Right? So here's the hypothesis here. We're trying to show that convert G actually does what it says, and if it does operate correctly and it's doing what we want it to do, then convert G will be equivalent to G. Okay? And I'm going to put that a different way. Because we've proved that, well, we're in the process of proving that that a GNFA is, well, an FGA. Well, look at my terms. Let's see. I'm probably getting a little tired. Need to eat. A GNFA and a D. Sorry, we're trying to prove that a DFA is equivalent to a regular expression. So we went from a DFA via GNFA to a regular expression. So so we're trying to show that GNFA is equivalent to G, and we're using convert as the means to do that. So effectively we're trying to prove that convert is equivalent to G. If you follow that logic, that's sort of essential. Okay, so now we concentrate on the inductive proof of this statement. In other words, that convert G is equivalent to G. Now, how to do that? Now it's more than one square. It gets a little difficult. Let's say now we're probably entering M1 master's level in terms of level of abstraction. All right. Okay, so let's take the starting case, the basis case, which is our lowest level possible. That's when k equals 2. And k, remember, k is the number of states in your G, in your GNFA. Right? Well, if k is 2, then there are only 2 states. Right? G only has 2 states. In other words, they have to be the start state and the accept state. And that means there's only one transition arrow. Okay? And what's on that transition arrow? Well, a regular expression. And how do you interpret that regular expression, R? Well, it defines the... Now, what does a regular expression do? It describes the language. Okay? And in this case, there's only one transition arrow. So, and it goes from an accept state to... Sorry, it goes from a start state to an accept state. Okay? So anything that's on that... like any string that matches that R on the transition arrow to the accept state, that string is accepted by the machine G. Okay, so that means that machine G recognizes that language, all those states. All those strings that match the R. So whatever G is, all the input strings that G recognizes, in other words the language, they will go immediately from the input, from the start state to the accept state directly, right? And because you go just in one step from the start state to the accept state. And which strings get matched by the R? Well, all the strings that got accepted by G. Okay. Well, that means that the language that the R, the label on the transition arrow, that's the same language as the language that the G is accepting. In other words, they're equivalent. It's getting tougher. If you had trouble with that, well, two things you can do. Consult the text, just read it over. Get Sipser's word for it rather than mine. Although, when it gets tougher, I tend to paraphrase much less. I tend to be more literal and just quote him, use his words and so forth when things get tougher, and things are getting tougher. So your two options: one, rewind, or two, consult the text, or both. Okay. All right. Now the inductive step. Now it's induction, so you assume it's true.